Okay, my name is Kanat Tulen. I am from Kazakhstan. So first of all, I would like to thank the organizers of this workshop. Especially, we would grateful to the professor Alexey Karapetyan's for giving us an opportunity to give a talk here in this workshop. The title of my talk is Optimal Range for the Hilbert Transform in Marcikiewicz Spaces. This is a joint work with Australian mathematicians Fyodor Sukochev and Dmitry Zanin. So this is just contents of my talk. So let I mu denote the measure space. I is a half line or the set of real numbers sometimes. We denote by Li mu the set of all Lebesgue measurable functions, and define L0 to be the subset of these Lebesgue measurable functions, which consist of all functions satisfying this condition. This measure is finite for some positive number s. Then for any f from L0, we denote by f star the usual decreasing rearrangement of the function f that is defined by this formula. So then we say A is a symmetric quasi-Banach function space on I if the following conditions hold. First, E of I is a subset of L0, and the second, E of I is a quasi-Banach with this quasi-norm. And the third condition is if F is from E of I and G is from L0, satisfying this estimate, this inequality, then G must be from E, and we have this norm estimate. So it is well known, LP and also Orlich, Marcikiewicz, Lorentz, and some other spaces are basic examples of these symmetric spaces. More details on symmetric spaces, or in English books it's called sometimes rearrangement invariant Banach function spaces. We refer the reader to these books. So if E is a symmetric Banach function space, then for S, for any S, we define the dilation operator ds by this formula. Then the upper and the lower Boyd indices of E are the following numbers. These limits exist for any symmetric spaces E. Moreover, they satisfy this inequality. So it is easily checked that if E equal to LP space, then we obtain that the upper and the lower Boyd indices equal to 1 over P. So also let phi be an increasing concave function, which satisfies that phi 0 equal to 0. Then the Lorentz space is defined by setting. This is also an example of symmetric Banach function space. In particular, if phi equal to logarithmic function, we denote lambda phi just by lambda log. And further define the space, which is called weak L1 space. This is defined by this setting. This space is quasi-Banach space with this quasi-norm. So in the literature, in the books, this space is called just weak L1 space. And for each f from lambda log, we define the operator S, which is defined by the formula 1.2. This operator is sometimes called Calderon operator, and then it has close connection with the Hilbert transform. So that's why this is important tool in our research. Also, if f is from lambda log, we define the Hilbert transform, which is defined by the principal value integral, or in the sense of principal value. So our result, so our research is was started from the thesis of a Canadian mathematician Boyd. In his thesis, Boyd posed a problem of finding necessary and sufficient conditions for the Hilbert transform H that to be bounded from one symmetric Banach function space into another. So in his thesis, he obtained the following necessary condition of the boundedness of the Hilbert transform. So this result, and he also obtained a necessary and sufficient condition, but in the case when E equal to F, so from one symmetric space into itself. So he obtained the following result. The Hilbert transform H is bounded if and only if the Boyd indices satisfy this condition. In this case, well, Boyd indices are called non-trivial Boyd indices. So he also obtained the following result. The Hilbert transform H is from H is bounded from E to F. So here E and F are symmetric Banach function spaces. If and only if this Calderon operator is bounded from E to F. So later Anderson also obtained the discrete version of the Boyd result for the following discrete Hilbert transform, which is defined by formula 1.3. 1 minute? Okay. So, but we know that Kolmogor's result, which says that H, the Hilbert transform bounded is from L1 to weak L1. So, okay. So, later in 2001, the Komori obtained the discrete version of Kolmogor's result for the discrete Hilbert transform. So we studied these problems first. First problem says, given a symmetric quasi-Banach function space, why we consider it a quasi-Banach, because we want to obtain more general result, which includes Kolmogor's result. So the second problem, also the discrete version of this of the problem 1. So if we define, let us given E a quasi-Banach symmetric space, then we define the following space F of R plus with this quasi-norm. So, and the following theorem provides the solution to the problem 1. So if E be a quasi-Banach symmetric space on R, if this condition holds, then so defined F of R is a quasi-Banach symmetric space. Moreover, this space is the least or smallest symmetric quasi-Banach space. We call it optimal range, such that the Hilbert transform is bounded from E to F. So this result was published in this paper, and the answer to the second question, so the discrete version of this theorem, was obtained in the paper, second paper. So then we asked ourselves that what gives this abstract theory. So in fact, this gives us the following result. So if E equal to L1, then our optimal range, so the smallest quasi-Banach symmetric space, is in fact the separable part of weak L1 space. Here, L1 infinity 0 is defined by the formula. So this is a closed subspace of weak L1 space. So then we considered that if E equal to Lorentz space, so is there any Lorentz space equal to F? So this result was investigated separately because of its proof was difficult. So we published this result in this paper recently. So our aim in this talk is the question of, so the dual question to the above question, so Marcikiewicz spaces. So if E equal to Marcikiewicz spaces, then what is the smallest Marcikiewicz space that equal to F? So Marcikiewicz space is defined by this way. So similarly, phi is equal increasing concave function satisfying this condition. Then we define Marcikiewicz space as follows. This is also an example of symmetric Banach function spaces. So if phi be a concave function satisfying this condition, then define a function psi by this formula where operator S is defined, so Coulomb operator, which was defined in the formula 1.1, I think. So this is our lemmas. Let me skip it. So this is our final result, which says that, which characterize optimal range in Marcikiewicz spaces. So this is our corollary. This is an example of when Boyd indices are trivial. So why this example is so important? Because when phi equal to log, this Marcikiewicz space is very important. So it has many applications in the non-commutative geometry of Alan-Kohn. So thank you for your attention.
Thank you. About questions, speaker?
So you have if and only if result only in case of Lorentz space, right?
Yes.
In other cases, we have result if then, right?
No, in all cases we obtain if and only if.
In all cases.
Yeah.
But in your theorem, you stated that if something, then I don't see in general theorem if and only if.
I can reformulate this. One moment, please. In this case, we also obtain in Marcikiewicz case. This is also if and only just a moment, please. This is Marcikiewicz spaces.
More questions? No, then